Greetings, welcome. So in this video, we're going to talk about one-wire transmission of power. There might be a part two to this, but part one's all right as well. What do we mean by one-wire transmission of power? So normally, you have a battery, the positive, the light bulb that goes around, and the line to the negative. And that's how it goes. So what if you just have a wire coming out and you get voltage showing up that you could use as power? That's a bit different, isn't it? And so one way I'd heard of getting at this one wire transmission of power is through something called an Avraменko plug. And that's, one diode this way, the other diode the opposite way off of the end of a coil. And you can see something there. That's not the best way to do it. I hate to mention Tesla because I don't know a lot about him, but you can see this in his patent where he's got, a bifilar coil and the other wire is going out to someplace distant, and then he sets up the same thing again. So he transmits it with one wire. So again, you can see this. We're not doing it in this video. You can see one wire transmission with an Avraменko plug. Again, I don't think that's the best way to do it. The way to do it is you have a primary and you also have your secondary. Now, conventionally, the secondary would be hooked up to both ends of your secondary coil. If you want to draw power like through a bridge rectifier or something. And we demonstrated in, I think it was just the last video or a very recent one, when you have that, the primary, and then you put the other same size cap, same size coil on the secondary, you can see voltage show up in both caps, just matched, perfectly amplitude matched, phase matched. They're just zooming along there. And so then it's like, okay, well, let's take it apart. So you take off one end of the secondary, and most of the voltage in the cap is still there. I mean, it's not subtle. So again, I don't think the Avraменko plug's the best way to do it. This is like, it's like boom, it hits you right in the face. It's right there. And you haven't, it's almost like half-wave rectification, but you get even more. So let's just demonstrate it, and then you can think about, is there anything you want to do with it or something like that, and go forward from there. So I had a lot of fun with this. We'll probably make a part two. I'm still thinking about that. I got to look at that some more, but let me stop blabbering and I'll just show it to you. Here we go. So here we're going to return to our bifilar coil, this 8-inch by 8-inch bifilar that I showed previously. I mean, it's not perfect. It's got some problems, but it, good enough. So it's mainly just, two wires, one right on top of each other going up here. And we're taking one of the strands and we're putting it where, after this cap gets charged up through these two bus lines, through those two solid state white relays, this cap gets charged up, and then it gets discharged when a connection is made between here and this leg. So you have a connection, these two are joined, and then this one connects and the power goes zoom, 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 right around through there. So I'll put in a 4 nanofarad, 0.004 UF cap. And we're still, where am I here? We're still only running at about 30K. Because it's around 7, it might be 7.5 millihenries. And this could go faster before it runs into significant proximity effect or skin effect. So the Q factor could be even higher. I think you could go out to 60 or 90K before you start running into a problem. We're not running that fast yet. But I don't know. I might have some some 1 nanofarads. I don't know. This is small enough. So let's just fire it up, and you can see the oscillations there. We got 12 of them, and it's ringing pretty well. So let's set it up as we did in a recent video. So I've connected the other coil, the secondary, to another cap of the same size. I've hooked up another channel on the oscilloscope, and when we turn that channel on, we see they match up just about perfectly. And I demonstrated all this in a previous video. And so we also see I've put this white line to one end of our cap, and I can put a resistor in and dampen it out. I'm just going to short it out, and what do we see? That's what we see. Boom. It knocks out both this one and the oscillations in your first cap. Boom, boom. So, end of story, huh? So let's take this darn thing apart. Wait a minute. I'll just pull this out and kaboom. It's not exactly subtle. Let's, no, wrong way. I always do this thing. There we go. Looky there. Not exactly subtle. So my first thought was, well, maybe I didn't have both parts of the oscilloscope hooked up, because, you know, if you like leave the negative off and the positive's just floating around, you see all kinds of crazy stuff. But no, they're both hooked up. So that's saying that that voltage in the second cap is real. And there is only one wire flowing there. There's no return path or anything. That's just one wire. It's like, you know, you can imagine someone taking it apart and, well, it's still running for the most part. Now, it doesn't get the positive half that well, and there's a lot, you know, the two ends of the coil, we'll put the other end, they behave much differently. But there's this one, so before I forget, let's go ahead and short the cap again, just like we did before. Kaboom. Looky there. Now the frequencies may be a bit different, but the oscillations are still there, and it's behaving as though it's out in the far field, as though there's no problem. So when you're drawing off from here, it's not affecting the Q factor of the first cap. So let's take it off. Yeah, it changes the frequency, but the Q factor looks about the same either way. Now the other thing, and in a moment I'll try and show that there is real power coming out of there. We'll set it up with a Abromenko plug. He's Russian. Actually, he might be Ukrainian. I don't know. I can't tell them apart. Poor souls. What was I saying? There's so many weird things here. So here, your first cap is charging up. There's no galvanic connection to the other one. It's just sitting there as a secondary, and somehow it charged up halfway. I guess that's because it's just one wire. Now here's an interesting thought. I can't get at this because it's too fast. We need more induction, Captain. The engines are buckling. But if I had 10 times as much induction and or, you know, could get a similar Q factor with thicker wire, just shut the Fokker off right there. So now you've gone from 10 to, I mean, it's saying like -10, but it's probably like -9.8 or something like that. And this one's at 9.8. Then just do what you want with that one. And then flip the thing over and pulse again. And, you know, here it's kind of doing a half wave thing because it's one wire. But, you know, with the pulsed over, you get the same thing going on right here. That should work. You know, it'd be a lot of work, and again, you're probably just better off buying a solar panel from Harbor Freight. But boom, look at that. That's down to there. You know, when I was sorry, I'm kind of rambling, but when in the, I think it was the last video, I was looking at the far field, and I have trouble getting the things lined up. Everything's lined up beautifully. So unlike, you know, with the far field, where you get the same effect where when you're pulling stuff off, it's not dampening out the oscillation. Here, everything's just lined up for you. And the only problem is it's going too fast. You're not going to see this unless you opto-isolate everything. If you have a transistor, you're going to have a path to the Arduino ground or whatever, you know, you're using. You're going to have a path to ground, and it just damps out the oscillation. You don't get these oscillations. So you have to have things isolated. Now, how can you do that? I'm using opto-isolated relays. What are the other ways you could do that? Well, you could use a physical relay. Now, a physical relay is going to be about 20 times as slow. You could use a reed relay, maybe like 5 times as slow, or a reed switch, maybe 3 times as slow, and you know, it's also going to be kind of jittery. So this is your best bet, is opto-isolated relays. What's one other way where you can get isolation, you know, not opto-isolation, but an actual air gap where, you know, you boom, and then you have an air gap. There's no galvanic connection back to source. A spark gap, right? So spark gap, and then it's boom, it's gone. And that lets the thing ring around, and you'd be able to do all the same sort of stuff and have the same sort of effects going on. Now, with the spark gap, and you know, unless you're like Tesla or something, I mean, how the heck do you control something like that? And you know, he didn't have oscilloscopes. So how the heck do you know what you're doing? I mean, he did, of course. So it's nice to just stay with these relays, but about the quickest you can go is 100 microseconds. And I don't know what we're on here, 25 microseconds. And so, in other words, we need about 10 times more induction. So what if we hook up an earth ground to the other side? This adds another layer of complexity. I'll show it to you and you think initially, oh, that sucks. And then we fiddle around a bit and it's like, oh, wait a minute. So here's our earth ground. Ah! Get-o! So here's our earth ground line, and here's the other end of the coil. When I connect it, oh, connect. Come on. Just a minute. Ah! It does that. So at first glance, it's like that sucks. There's an interesting thing though. This coil, because it now has a connection to ground, can continue to oscillate. The phone was going dead, so I'm not sure where I left off. Oh, come on now. All right, we're back. So what I've done is I've connected the ground to the other line. You know, we just got one wire going there, and I've connected the other side of it to ground. And what that's letting it do is it's letting the second coil here continue to oscillate. You know, this is while the thing's off, while the cap is charging. I mean, charging there and then off. It's oscillating all the time now with ground. And again, it's fascinating to me that 5 volts shows up here when you charge this other cap to 10 volts, but there's no galvanic connection between the two caps. So I don't know
I need to get I need to get some small milliamp microamp meters and see if it's drawing any more current. I can't tell from here, but it I don't know. It's kind of hard to see how it would. So now it's oscillating all that time, and it's not a small. You got a big swinging Johnson there, and so you can start to think about messing around with the timing here. So what I'm going to do now, let's just have the cap charged for 135. I mean, the cap's full at probably like 50. So I'm just sort of changing where this thing, with the turn on and the turn off, where that happens. So 135 and compile. Now what do we see? That's what we see. That's kind of interesting, huh? Yes, it is. So you don't even really need this earth ground as long as you can slow it down, but you start to get some interesting stuff once you have the earth ground in there. Now I've removed it, and that's what it looks like. I'm not going to do the Avermenko plug now because this is getting too long. I'm talking too much. I might do the Avermenko plug. That's just to show, I was going to do an Avermenko plug and put it into like a 10 UF or 100 UF cap and show, look, there actually is power flowing. But you can see it. I mean, I had both ends of the oscilloscope hooked up. And so that's really what's going on there. And again, you just got one wire. And when you just have the one wire, it behaves much like it's out in the far field, except for all the things that you want lined up there are lined up. There's much more to look at on this. Let's stop here. So now you know what one wire transmission of power is, and you can see it. This is easy peasy to set up. You just need to make sure you're using opto-isolated relays so that this cap can ring both positive and negative. They need to be AC relays, and you see it. Again, it's not subtle. So thanks for coming along, and stay healthy, and until next time, have a wonderful springtime. Okay, bye-bye.